All right, so welcome back. Welcome back to this channel. So in the last video, we have looked at stable diffusion, right? We have looked at conditional image generation. How can we take a condition and use a like. All right, so we have learned about conditional image generation. So how can we actually add like conditions? How could we input text embeddings for these images and get this output? So in this video, we are going to look at how can we actually decrease the number of inference steps it takes for us to actually generate an image. I'll probably cover that. I'll cover I'll cover the concept of inference steps. I think I haven't already before in the previous videos. I'll probably cover that in this video. And then we'll also try to see how can we reduce the number of inference steps by using by reading some papers, by you know copying the ideas of some papers that have already been released. I'll share the papers. I'll share the link of these research papers in the description. Make sure to check them out. And even if you could read it, try to read it. All right. So I'll be going through the basic things. There are like a lot of mathematical equations in the paper, and I think for now we will not be needing those equations because they just depict like the derivation of loss function and all that. But we just have to understand like the basic things, like why do they work. So let's get started. So first, in the last video, I'll just cover up the whole basic idea of stable diffusion, right? So we'll just have like a unit, right, which will take in some noise. We'll just take some noise, right, and then we'll try to subtract, or we'll just try to predict some noise. For example, I'll just delete all of this. I'll probably write some good figures. So we'll take in some noise image. So this is the training step. So in the training, we'll have like small patterns and we'll just add a lot of noise. And then we'll pass that through a unit. And the unit has to figure out all of the noise that it has to subtract from this image, right? So it'll just take this and subtract this. And then it will get this image, 9 image. So this is the training time where we have the feature or the features of 9 inside this image, inside this input image. But in the inference time, we'll use random noise and let the model figure out some patterns that it might feel that it may be from a given distribution. So we'll be doing that in the inference time. And while in the training time, we'll just add a lot of noise to actual training data images, and the model has to predict this noise such that the difference or the subtraction of this and this matrix and this matrix will be equal to this 9 or this image. So that is the idea. When we'll just use MSE to actually predict this noise while training, and in the inference time, we could actually taking random noise and predict random noise that you have to subtract and hopefully get some features that may replicate that of the training distribution. So that is the idea of stable diffusion, right? This is how we do stable diffusion. But in reality, we will not just subtract. We'll just not just predict one image, and we'll not just get the complete image in just one step. So this is just one inference step. We'll use this unit on like this is one inference step. In the real world, while we're actually training those models, while we're actually predicting like sophisticated images, the output of this will be something like this. A lot of noise would be removed, but there will still be so much so much noise. And in fact, you have to send this to the unit again, and then have to predict it again, maybe something like that. And you have to do that multiple number of times to actually get this actual image that looks pretty good. And this is actually the idea of inference steps. So this is like one inference step, and we'll perform multiple of these steps to actually slowly pass in this image the difference of this previous processing, if there is. And so we'll first pass this random noise. Sorry, I'm going in the inference time, we're going to pass this random noise into the first unit or the unit for the first time. And then we're going to get an image or noise, and we're going to subtract this noise from the original image. We're going to get this value, and we're going to pass that to the same unit again to actually predict the next noise from that image, and we're going to do that multiple number of times to actually slowly remove the loss step by step, and this is actually called the idea of inference steps. And while we are actually predicting like realistic images, it will take a lot of inference steps. For example, 60, 70, 80 inference steps. In that time, the model might get very slow, pretty slow, right? Even though we could use auto encoders, like we could use like latent latent space vectors, we could just convert them into like we could just use an auto encoder to actually convert them into some latent space and use that. Even though we'll do that, the model might get pretty slow, when we're actually building like multiple images, predicting multiple images. Stable diffusion might be pretty slow, and that is where um, a research paper has been published. I think it is called Progressive Distillation for Diffusion Models, right? In which they propose a very theoretical and very intuitive idea, in which a trained model, just like the previous one, just like the previous models that I have described in the last videos, where we're going to have that model, and that model is actually going to be the teacher. So that is a teacher model, and the teacher has a lot of experience, right? So that is the teacher is trained on multiple data, so much of amount of data, but the teacher is pretty slow, right? That is why we have many inference steps. So the teacher is going to have many inference steps. It's going to take many inference steps to actually go from complete noise, to predicting or finding some patterns in these images. It might take a lot of inference steps. So we're going to propose a student model in which the student will learn from the teacher, but the student will be faster because it will learn from the first prediction to the n+2 prediction. I'm going to cover that. I know you might have not got that. I'll just cover that here. So first, you don't have a teacher model, which is a unit, right? It is going to take in some random noise, right? It is going to predict noise. I'm not going to draw that architecture. So let's say it is going to predict some type of. So it takes like, so let's say this is the image. I'm going to draw some images. Right. So let's say this happens. So these are all the time steps, right? So first, at the first inference step, this noise is taken, and the teacher is going to predict the noise that should be subtracted. That it will subtract from this image. It will get this image. It'll get this image. It'll take this image into this teacher model. The teacher is going to predict noise, and we're going to subtract the noise from this image to get this image. And we're going to do that for multiple steps to actually obtain the final result. Whereas, so this is the teacher model. This is the main model that has a lot of experience, that is trained on like huge amounts of data, right? And then what we'll be doing is we will be developing a student model. We'll be training another student model, right? We'll be training a student model in which the student takes in this noise, and it is required to predict this image. Or for example, so there are like two losses, right? So the teacher has to taking this input image and predict the noise that should be subtracted from this to get to this. And then the model has to take, and then the teacher will take this also and has to predict the noise that should be subtracted from this, right? So there will be two separate losses that it has to predict. And rather than just predicting this image, it will try to predict, or it will try to sample this image, or try to predict the noise that should be subtracted to obtain this image. Or to make it easier for you, the student will just compare its output, the subtracted output, to this step. So it will not just, here the teacher went from this to this, but the student will go directly from this to this. And then at the same time, we'll train that, and then we're going to take this image, and we're going to go from here to here, and go take this image, go from here to here. Right now we have just half the number of steps. So the idea is, in the teacher model, we're going to have a unit model, which is going to have like these many number of training steps, which is going to slowly subtract the noise. But in the student model, while training the student model, we're going to grab this output of the teacher model. So the teacher model, let's say it predicts on some noise image, or in the training set. So there will be lots of training images in training set, right? It will take this training set and try to slowly, over the number of inference steps, try to decrease the loss. And then it will have like, let's say 9 or 10 predictions, 9 or 10 training steps. We're going to take the student model and we're going to get, we're going to take the first input, the noise input, and going to and directly go from here to here, directly compare our output of the student model with this output. So we'll be doing a MSE loss. We're going to have like a mean squared error loss between this image, the output of the student image, and not this image, but directly this image, to actually make the model faster. It could actually go from not just subtracting noise 1 and then separately noise 2, but it will combinedly separate, or it will combinedly subtract noise 1 plus noise 2. Yes, that is the idea. Rather than subtracting them or predicting these noises separately, we're going to predict the sum of all this loss at the same time. We're going to predict the sum of both the losses, both the noises, not the losses, noises. So that is the idea. That is the idea of training this teacher student model. And again, we're going to, let's say, take this image. We're going to predict this image, let's say. I'm going to predict this image. And we're going to finally predict this image. Right? We're going to have, we have achieved 4 steps. But what we can do is, for more sophisticated models, we could train another student model. We could train another student model that is just going to go from here to here, right? It's going to take this input as image, this input image, and just directly go from here to here. And that might be possible. I mean, to be honest, like for sophisticated architectures, you don't have like one training step. You'll not just take in loss and predict directly. But we could actually decrease the number of steps it takes for the model to actually predict this output image. So that is the idea. We'll be training the student models. So we'll first train the teacher model on all of this data. We are going to make the teacher model predict on all of this training data set, right? And then we could just add the student model, grab the student model, give it the same inputs, the same input that we gave to the training model. And we are going to ask this student model to actually predict the second, not the first, but directly predict the second output of this teacher. And then we're going to take this second output of the teacher that the student model predicted, and we're actually going to compare both of these, right? We are going to compare this and this, and we are going to reduce the loss such that both of these values are pretty similar. And we're going to compare this and this, and then this and this. So that should make sure that we make our model sample faster. All right. So yeah. So we're going to have this architecture, this intuition. We're going to follow this intuition to actually train student and teacher's model, teacher and student model, to actually sample faster, to actually predict the image faster, get to this image faster with lesser inference steps. So this is the one paper that is pretty good. And the other application of this distillation or this method is actually in classifier free guidance models. I'm going to tell that. I'm going to come back. I'm going to come to that in just a minute. So the idea of classifier free diffusion models, I think. Yeah, diffusion models is, we're going to have like, just to make sure that for example, right? I'm going to give an example. Let's say there is you get some model text to the model. So let's say this is the prompt for the model to actually predict. So let's say photo of maybe anything, maybe something like photo of Dhoni, maybe something like bowling, maybe something like that. Maybe Dhoni not bowled. Yeah, maybe hit. Okay, don't care. So let's say this is we want the model to actually predict this, predict from this prompt. This again, the photo. There is no need of photo to actually exist. There should be a photo of Dhoni separately. There could be a photo of bowling separately in the training dataset, maybe somewhere in the training dataset. And we are going to predict that. So first we are going to pass that through encoder. we're going to get a feature representation somehow, right? And then we could just and then what we'll do, what we'll be doing is we're going to so we're going to have this output, right? We're going to have this feature encoding just to make sure that the model is creative and the model is diverse. For example, if the photo of Dhoni actually existed, we don't want the model to actually make the image as close as possible to this actual image. So we want the model to actually be creative, right? We want the model to actually be creative. So that is the idea. So what we'll be doing is, just to make sure the model is creative, we'll just take this random sentence, or just empty sentence, empty sentence. We're going to create a feature encoding, some arbitrary random feature encoding, and we're going to pass both of these. We're going to concatenate both of these in like so we're going to have like, if this is like n by n or n, and this is n, it is going to be 2n. So we're essentially going to have two vectors but combined, right? We're going to pass that through the unit, right? And as a result, we're going to have like other side, we're going to have like two outputs. We're going to have two images. We're going to get two images, right? We're going to get this image, one image of for let's say Dhoni. So we're going to get the image of this prompt. Yeah, maybe something like that. Yeah, I'll probably try this, right? So maybe you get this image, and again you'll and for the empty string you'll get an arbitrary prompt or something like that. Yeah, and what we'll be doing is we'll just calculate the weighted average. Weighted average is nothing but giving more importance to one factor. So we'll be calculating the average, but we'll be giving some more importance to specific vector or a specific value, and the ratio or the value that represents how much importance we should give for a specific value. In this case, is called the guidance scale. So it determines how much importance to the prompt the model has to give. It is a hyperparameter. You could just adjust it as per your need. So if the guidance scale is more, then the input prompt is going to affect the output of the model by a lot. So we'll just calculate the weighted average, and what we'll be doing is we'll just pass this weighted average through we'll just get this weighted average, and we'll just pass this through like this layer. So we just concatenate all of this, or we could just do that all again. So this is a problem. This is a problem that has been carried out. This is actually a problem, right? Just to make sure that, so the idea of this model, the idea of this architecture is to actually make sure that there is the model should be obedient to the prompt, and at the same time it has to be diverse. So that is to make sure this happens, this for a phenomenon doesn't take place, we're going to do this. And the guidance scale is going to specify how much importance it has to give for the prompt image or the arbitrary image. And then we'll be passing, then after the weighted average, we're going to pass that we're going to make that into the specific shape that we'll be requiring, and we'll just pass this to the unit again, and we can just get this. So this is actually a problem. This is not connected with our video training faster models, but the same architecture, so the same student teacher architecture is actually used here, in which, right, we'll have a teacher which is going to predict like multiple images, right? It is going to have for example, it takes in a prompt, it takes in some arbitrary prompt, and right, it's going to have some noise, it is going to take in some noise, let's say. It is going to predict some images, maybe something like that, probably something like, yeah. And then, after a long number of times, after a long number of steps, hopefully the teacher predicts this, right? And then the student model, right, is going to take in the noise image. It's going to take this noise image, the noise. It is going to take in the prompt, and it's also going to take the guidance scale just to make sure it understands. So the student model is actually going to find the patterns, find the relation between all of these values, and it will actually be able to go from this maybe to this and maybe to this directly, or not a very accurate diagram, but maybe go from here this to this and maybe this, right? So it will be able to sample faster, and it will also be uh like updating this guidance skill, right? So just to or based on the guidance skill, so it can understand how this guidance skill actually affects the model, and that is a very good thing, right? We don't have to train it separately. The model identifies the so based on the guidance skill, it is going to predict this output images, and and this is the student model is again going to learn from this teacher model, and again you can have as many student models as you can. And for example, this student model, so let's say I create another student model. This student model is actually going to train on this student model. So this student model is going to become the teacher, and this will be the student model. So that is the that is the ideas of that is the idea of like distillation in uh, in generative adversarial networks. Distillation is actually a concept in, I think, chemistry. I'm not good at that. But okay, so this is the idea of distillation in machine learning, in deep learning. If you are a chemistry teacher, you might be pretty angry with me, but so that is the thing. Thank you for watching. Next video, we'll cover something else. So thank you for watching. See you in the next video.